Parallel reactions. Parallel reactions is actually coming under the complex reactions. So parallel reaction means two reactions are taking simultaneously or side by side. So these reactions, the reactions in which the molecules react or decompose in different ways, giving different products. That means the same reactant reacts in two different ways, giving rise to two different products. So the reaction which is giving highest yield is called the main reaction, and the reaction which gives smaller yields of products are called the side reactions. For example, when we are considering a reaction, that is reactant A is giving two products B and C through two different pathways and having two different rate constants. So if we are considering the reaction A giving B, and the rate constant will be K1, and for the reaction A giving C, the rate constant will be K2. So if K1 is greater than K2, we can say that A giving B is the main reaction and A giving C is the side reaction. Similarly, we can have the second situation, that is when A giving C, that is the K2 is greater than K1, then A giving C will be the main reaction and A giving B will be the side reaction. And if we can have a situation where K1 and K2 are equal, then these reactions are actually called parallel reactions. Okay. So, parallel reactions എന്ന് വെച്ച് കഴിഞ്ഞാൽ നമ്മൾ ഏതെങ്കിലും ഒരു റിയാക്റ്റന്റ് രണ്ട് രീതിയിൽ രണ്ട് പ്രൊഡക്റ്റ് ആയിട്ട് മാറുന്നു. അതിന് രണ്ടിനും സെപ്പറേറ്റ് റേറ്റ് കോൺസ്റ്റൻസ് ഉണ്ടെന്ന് അസ്യൂം ചെയ്യുക. ആ ടൈപ്പ് റിയാക്ഷൻസിൽ നമ്മുടെ റേറ്റ് കോൺസ്റ്റന്റിന്റെ വാല്യൂ അനുസരിച്ച് നമുക്ക് റിയാക്ഷൻസിനെ പാരലൽ റിയാക്ഷൻസ് ആണോ സൈഡ് റിയാക്ഷൻസ് ആണോ എന്ന് റെപ്രസെന്റ് ചെയ്യാനായിട്ട് പറ്റും. നമ്മൾ ഒരേ റിയാക്ടന്റ് രണ്ട് രീതിയിലേക്ക് മാറുമ്പം രണ്ടിന്റെയും റേറ്റ് കോൺസ്റ്റന്റ് ഈക്വൽ ആണെന്നുണ്ടെങ്കിൽ ആ ടൈപ്പ് റിയാക്ഷൻസിനെയാണ് നമ്മൾ പാരലൽ റിയാക്ഷൻസ് എന്ന് പറയുന്നത്. ആ റിയാക്ഷൻസിന്റെ റേറ്റ് കോൺസ്റ്റന്റ് ആണ് നമുക്കിനി കണ്ടുപിടിക്കാനുള്ളത്. സോ എക്സാമ്പിൾ ഫോർ പാരലൽ റിയാക്ഷൻസ്. Normally, these reactions are taking place in the case of organic compounds when we are functionalizing or reacting a reactant, for example, phenol, and we are nitrating the phenol. And there will be two preferable positions, that is ortho and para. So we can have two products, ortho nitrophenol and also para nitrophenol. In this case, one will be the major product and other will be the minor product. So the major product or major pathway is called the main product. So in the case of nitration of phenol, we are getting orthonitrophenol as the main product and paranitrophenol as the side product. Similarly, in the chlorination of benzene, if 1 mole of chlorine is reacting or added to the benzene, we will get monochlorobenzene and HCl as the byproduct. But if we are considering 3Cl2, that is 3 molecules of chlorine are added to benzene, then we will get the benzene hexachloride, that is BHC. So these are some examples of parallel reactions. That means the reactions which are taking place in two different pathways having two rate constants. Now the rate expression for parallel reactions. So first of all, our consideration is A giving B and C, and it is having two rate constants K1 and K2. So initially at a time t is equal to 0, the concentration of A is given as A, and we are assuming that only reactant is present in that situation and the concentration of product is 0. So in order to derive the rate expression, we are considering the initial stage of the reaction, and at that stage the concentration of both the products are 0. And after a time t, if the concentration of A changes to A minus X and the concentration of B is Y and that of C is Z, and again we are assuming that the amount of substance changed will be the sum of the product, that is X is equal to Y plus Z. Now, since A is converted to two products, we can represent both the steps in terms of change in concentration of the A. That is, dx by dt is equal to minus d concentration A by dt. That is only A is changed. which is equal to, through the first pathway, we can have the rate constant K1, that is K1A plus K2A. And we know that after time t, the concentration of A changed to A minus X, that is minus dA by dt is equal to, here concentration of A is common, so we can take A as the common factor, then K1 plus K2 into, after time t, we have the concentration as A minus X. So the rate expression becomes dx by dt is equal to K1 plus K2 into A minus X. Then separating the terms, that is dx divided by A minus X is equal to K1 plus K2 into dt. On integrating from t is equal to 0 to t. Okay. We get ln A by A minus X is equal to K1 plus K2 into t. Now, we are converting this in terms of concentration of A. That is, this is the initial concentration and A minus X is the concentration after time t. So, we can easily convert in terms of concentration, that is ln A0, which is the initial concentration, and concentration AT is the concentration after time t, which is equal to K1 plus K2 into t. And this is the reverse, that is reciprocal, minus ln AT by A0 is equal to K1 plus K2 into t. So, we have AT by A0, that is the ratio of concentration of the reactant at a time t to that of initial concentration, is equal to e raised to minus K1 plus K2 into t. From this, the concentration of A at a time t can be calculated as concentration A0 into e raised to minus K1 plus K2 into t. Similarly, we can assume or we can calculate the concentration of B and also concentration of C. So, concentration of B can be derived as K1 by K1 plus K2 into concentration of A into 1 minus e raised to minus K1 plus K2 into t. And that of C is equal to K2 divided by K1 plus K2 into A0 into 1 minus e raised to minus K1 plus K2 into t. So, the ratio of the concentration of the products at time t is given as concentration B by C, which is equal to Y by Z, which is again is equal to K1 by K2. That means all these terms are constant. We have only K1 and K2. Since we have X is equal to Y plus Z. So, the percentage yield of B can be calculated from the equation concentration B divided by total concentration of the product, and percentage yield of C is given as concentration of C divided by total concentration of the product. So, this is the expression for the parallel reaction.